Hello, everyone, and thanks for joining my live recording. Hello, everyone. Hello, everyone, and thanks for joining. Hello, everyone, and thanks for watching my videos. Today, we're gonna be covering fundamental of chemical kinetics in this video, a topic of general chemistry 2. And it's a very important topic of chemistry, in particular relate to the chemical reaction, the speed of the chemical reaction, how chemical reaction take place, and the reaction mechanism involved in a given reaction. So this topic is very important because, again, you need to know, like thermodynamics will tell you if the reaction require energy or release energy. However, it's not going to tell you how fast that reaction will take place. Chemical kinetics will study or research will basically give you an idea about how fast this chemical reaction will be. So again, studying this topic is fundamental to understanding the behavior of the chemical reaction. So without further ado, I hope you enjoyed the video. Thank you. What's chemical kinetics? How fast does a reaction proceed? What's thermodynamics? Does a reaction take place or not in terms of energy? So thermodynamic is going to tell you if a reaction will take place or not in terms of the energy involved in that reaction. If you recall, exothermic process versus endothermic process. So that's the energy needed for a chemical process to take place. But the thermodynamics doesn't tell you how fast the reaction is. Kinetics is going to be the science that you're going to study in order to determine how fast the chemical reaction is. And that's what we're basically introducing in this course, which is chemical kinetics. Chemical kinetics is the area of chemistry concerned with reaction rates, as I explained a minute ago, and the sequence of steps by which reactions occur. How the reaction take place? The reaction is not just a simple one-way reaction. Reactions are very complex in nature. The chemical reactions are not just one-step reactions. They are complex in nature. They take place through multiple steps, as we're going to learn in this chapter. Reaction rate is basically a measurement of the change in concentration over time. When you're driving your car, how do you know you're progressing? By looking into your speed, 10 miles per hour, 20 miles per hour, 30 miles per hour. This is how much distance you are basically traveling per certain time. The same thing for the chemical reaction. How you determine if the chemical reaction is progressing? By looking into the chemical concentration, the change in the concentration of the reactant and product. This is how we know we have a progress. If there is no change in the reactant and no change in the product, you're not producing any product, there is no progress. So studying the change in the concentration of the reactant and product over time is the introduction into chemical rate or the reaction rate. So this is just showing you how this is done. So how you study kinetics? You need the time factor. So you have to introduce the time factor. In order to study rate, you have to include the time. Speed is distance over time. Rate is concentration over time. So you start with 0 time. So this is your starting point, which is the reaction did not start yet, which is 0 time. At 0 time, you have 100% of A. Your reactant is 100%. You start the stopwatch, you record the time is progressing as you see, and as the time progresses, your reaction is progressing. How do you know your reaction is progressing? Look at the reactant concentration over time. The reactant concentration over time is decreasing by looking at the color code of the reactant, comparing it to the color code of the product, until you reach almost completion. Look at the, again, after certain, completion time, your mainly product and less reactant remains. So can we follow this in a diagrammatic representation? And the answer is yes. Here is a diagrammatic representation about what we just seen. So what we just seen here, we can convert this into graphical representation by following the reactant concentration over time and the product concentration over time. Now, very interesting feature in this curve. This curve is known as concentration time profile. Concentration time profile. This curve showing you the reactant starting from 100% at 0 time. So at 0 time, the reactant starts from maximum. At 0 time, you have no product. So at 0 time, you have no product. At 0 time, you have 100% reactant, which is this case here on the left-hand side. As you progress, the reactant is decreasing and the product is increasing. And that's what you see in this graph. As you progress, the reactant concentration is decreasing and the product concentration is increasing. So now how you measure the rate? You have concentration versus time. Concentration versus time. You need to get the rate. The rate is the change in concentration over time. Why there is a negative for the reactant and a positive for the product? Because the reactant is disappearing. The reactant is decreasing in concentration. So your rate has to equal negative the change in concentration over time. And the product is increasing over time, which is appearing over time. So the rate will equal positive the change of the concentration over time. So what is the name for this? When you have reactant and product, we say this is the rate of appearance of A, and this is, the rate of disappearance of A. So what you're looking at right now is the rate of disappearance of A, and this is the rate of appearance of B. So this is how much B is forming at what rate, and this is how much A is disappearing at what rate. So this is giving me the rate of disappearance and the rate of appearance. Why? Because it's per 1 mole. When you have this here, that means 1 mole. So when you have a 1 mole, there is a specific name for that rate. When you have a 1 mole of A and a 1 mole of B. And that specific name is the rate of disappearance of A and the rate of appearance of B. Rate of disappearance of A and the rate of appearance of B. When you have a 1 mole of reactant and 1 mole of product. To summarize that, rate is a change in concentration of a reactant or a product with time. The unit is going to be concentration over time, so molar, which is the unit of concentration that we're going to use here, over time, which is second, so molar per second. So that will be the unit of rate. A change in concentration, again, that would be at any given time. You can look at A here at 10 seconds versus A at 20 seconds, and you can calculate delta A, which is a change in concentration. You can look at B at 10 seconds, you can look at B at 20 seconds, and you can determine the change in concentration. So you have data. This data is basically, you can measure the rate at any given, again, interval. Here's your delta T, which is 20 minus 10. Or you can do it between 20 and 30. You can do it at between any time interval, as long as you have the concentration of reactant and product. So you can calculate these two from the graph. Here is another example showing you that we can follow the reactant concentration by studying the visibility of that particular reaction. You can see from here that you can measure the absorption of that reaction. Why? Because it has a color change. So you can follow the reactant by different means. Some of them are physical means, some of them are chemical means, and this is beyond Chem 1 and 2. As I mentioned, this will be BChem. So we'll go over different methodology to follow the chemical reaction. For us here, the table already given to us, the data already given to us, But how you conduct this in the lab? For such reaction, you're going to follow the concentration of bromine. The bromine has this intense blue color, brown color, as you see here. And this intense brown color, as the bromine is consumed, you can see it's basically the color is getting, again, almost at the end of the reaction will be colorless because it's converted to bromide, and bromide is a colorless. So this is by following the color change, you can tell how the reaction is progressing. And how can you measure this experimentally? Using, again, absorption. So you can basically measure the absorption, and all what you need is a light source and a detector to measure the change in the absorption of this color. And why 393 nanometer? This is from studying the absorption spectrum. So this is just to know exactly where the maximum is, because you wanna run your experiment at the maximum absorption. And the maximum absorption is at 393 nanometer. So you can run this first to determine the absorption wavelengths, and then after that, you can measure the change in concentration over time. And clearly, again, the concentration will be directly related to the absorption, as you can see from here. So that will give you an idea about what's happening in this reaction. So this is just showing you an experimental way of looking into this data, which is how to find the concentrations. All right. So for us right now, I said you don't need to worry about how to do this. This will be given to you, as I will show you right now. The table will be given to you, and you'll be using the table immediately. So the experiment was already done, and you are provided with data. But this is how you obtain the data for this particular process or this particular reaction. All right, so for what we went here, this was 1 mole. This was for 1 mole. And this was the rate of disappearance of A, and this was the rate of appearance of B. How about if you don't have 1 mole? How about if you have A moles? You have A moles of A reacting with B moles of B to give you D moles of D and E moles of E. How you express the rate? Now you have different number of moles. You will have to include this number of moles in your reaction rate. So the reaction rate will equal -1 over the number of moles. Why negative? Because the reactant, 1 over the number of moles, dA over dt. So this is the formula for the reaction rate when you're using the number of moles. All I need is to divide by the number of moles and include the negative for reactant, positive for product. So this is a general formula to apply this formula. So how to apply this formula to determine the reaction rate for N2O5 or NO2 or oxygen? What will be the rate of the reaction in terms of N2O5? What will be the rate of reaction in terms of NO2? What will be the rate of reaction in terms of oxygen? You'll use this model here. Let's look at N2O5. -1 over 2, the change in N2O5 over time. Remember, the reaction rates should equal each other. The rate of reactant should equal the rate of product. When reactant is converting to product. So the rate of reactant should equal the rate of product. So the rate of N2O5 should equal the rate of NO2, should equal the rate of oxygen. So again, so -1/2 dN2O5 over delta T will equal 1 over 4, which is product. The change in NO2 over delta T, which equal 1 over 1, because this is, again, invisible one here, the change in oxygen over delta T. So if I know one of these, I can get the reaction rate. If I done the experiment and I was able to determine the concentration change for dinitrogen pentoxide or nitrogen dioxide or oxygen, I will be able to determine the rate. And this is what we're going to do right now. I'm going to show you how can we determine the reaction rate from a given table. If I give you the concentration time data, how can you determine the reaction rate? So here is an example where you're giving the concentration over time. The concentration of N2O5, which is the reactant, the concentration of NO2, which is the product, and the concentration of oxygen, which is the other product. So let's look at what we have here. We have the 0 time. Remember, the 0 time is the reaction did not start yet. So what do we have? We have 100% of N2O5. That's the maximum you can have of N2O5. You have 0 of NO2 because there's no reaction yet. Once you start the reaction, 100, 200, 300, so you're starting the reaction is progressing, the concentration of the reactant is decreasing. So as the time progresses, your concentration is decreasing and your concentration of product is increasing. So the concentration of the reactant is decreasing, the concentration of the product is increasing. So how can you determine the reaction rate? You have a data with any given point. You can use any of these points. You can use 300 second, 400 second. Here's the concentration of the reactant at 300 second and 400 second. From this concentration data, you can determine again the rate. So this is what we're going to do right now. You can do the same for the product. Here is the product concentration at 300 second. Here's the product concentration at 400 second. And you can use these values at this time interval. Or the same for oxygen. And you already know the model. You already know what the relationship. Here is the relationship. Your reaction rate is -half the change of concentration of N2O5 over delta T. And it's 1/4 the change of NO2 over delta T. And it's the change of oxygen over time because it's 1/1. So all of these will equal each other. So whatever you do here, your outcome will be almost the same. So let's look at N2O5. So here is N2O5. Here is the rate as I explained to you. The rate is equal -1/2, the change concentration of N2O5 over delta T. Here is the concentration of N2O5 at 400 second. So at 400 second, that's the concentration of N2O5. Here is the concentration of N2O5 at 300 second. So this is from the table. And don't forget there is a negative here, as I mentioned, because this is again because it's a reactant. If you don't put this negative, you're going to have a negative sign, and the rate cannot be negative. You cannot be driving -20 miles per hour. You will never reach your destination because you're going to the in opposite direction. The negative means you're going in the opposite direction. So it's very important to basically, or going in reverse. You're not really going the opposite, you go reverse, which means that you never reach that destination. All right, so right now you have negative, the change in concentration over time. And here's the concentration of N2O5 at 400 second. Where I get that from the table. Here's 400, here's the concentration. Here is 300 second, here's the concentration. And that will give you 1.9 × -5. Is that the reaction rate? No, that's not the reaction rate. Here is the reaction rate. You have to include the number of moles. What we just determined right now is the rate of disappearance. This is the rate of disappearance of N2O5. This is how much N2O5 is disappearing over time. 1.9 × -5 molar per second. So every second you have 1.10 - 5 molar disappearing of N2O5. That's what the meaning, physical meaning of this. Every second you have 1.9 × 5 molar disappearing from N2O5. And why is the rate of disappearance? Because it's 1 mole. See here, there is no coefficient. You have a coefficient because there is a number of moles. What is the number of moles? 2. So how you determine the rate? You multiply this value time half, which is, you see here, and that will be your actual rate. So your actual rate is 9.5 × -6 molar per second. This is how much is being produced of product, being consumed of reactant. So every second, you're consuming 9.5 × -6 molar, and you're producing 9.5 × -6 molar. This is the physical meaning of this number here. So this is your rate. It's the same, as I said, as you're driving your car. What is the physical meaning of 10 miles per hour? I mean, every hour you're driving 10 miles. You're crossing 10 miles in distance every hour. 20 miles, 20 again miles per hour. Same thing for the chemical reaction. The rate here indicates how the reaction is progressing. According to this value, look at that, 10 - 6. This is very small. That reaction rate is very small. So that the physical meaning of the number matter. When you have 10 negative 6, that means the reaction is slow. This reaction is slow. You are consuming 9.5 10 negative 6 molar per second, or producing 9.5 10 power negative 6 molar per second. Look at it either way, it's a very small number, which indicates that this reaction is slow. And this is how fast is your reaction, your chemical reaction. So how can we use this reaction rates to determine the other reaction rate of other reactant or product? So if you look at here right now, this is acetylene. So you're giving the chemical reaction, acetylene mixed with carbon monoxide and water, to give you, again, hydroquinone and carbon dioxide. So this is your reactant and this is your product. And the question is, how can you relate this particular reactant to the other reactant, which is the hydroquinone or the product? So here is your product, which is hydroquinone. Here is your reactant, which is acetylene. How can you relate the acetylene to the hydroquinone? The only way to do that is to do it through this relationship. This relationship will always apply. You will have to write it in terms of reactant and product and then relate them to each other. What I mean by that? I mean that half of the N2O5 over delta T equal 1/4 of NO2 over delta T. So this is how they're related to each other. So if you want to relate the NO2, you need to get rid of 1/4. If you need to relate the N2O5, you need to get rid of the 1/2. So if you want to relate these two, you want to get rid of the whatever factor that is next to it. So if you want to relate the NO2, then you need to get rid of 1/4. How you get rid of 1/4? Multiply the whole equation times 4. If you want to relate the N2O5 alone, you want to get rid of the 1/2. How you get rid of 1/2? Multiply the whole equation times 2. Of course, oxygen, there is no multiplication because oxygen already has 1. So this is how we relate the different reactant to different products in terms of disappearance and appearance. So in this example here, we're going to basically relate the two. So what is the relationship between the two, the reactant and the product? The relationship is the rate of the reaction for the acetylene is -1/2, the change in acetylene over time. What is the rate of reaction in terms of hydroquinone? The change 1/1, see here there is 1, invisible 1. So 1/1, the change in hydroquinone over time. So which one I want to relate right now? I want to relate the acetylene. I want to relate this acetylene without the coefficient, which is the rate of disappearance. This is the rate of disappearance of acetylene, rate of disappearance of acetylene, to the rate of appearance of hydroquinone. Here is the rate of appearance of hydroquinone. So how they are related to each other? Get rid of that 1/2. How you get rid of 1/2? Multiply the whole equation times 2. If you multiply the whole equation times 2, then the rate of disappearance of acetylene equal 2 times the rate of appearance of hydroquinone. So this is basically how they relate to each other. So one more time, you are giving a specific reaction. In that specific reaction, the question is asking to relate a specific reaction rate, the rate of disappearance of acetylene, giving you the formula already, to the rate of appearance of hydroquinone. Here's hydroquinone. So the only way to determine that is to use the relationship between the rate of the reaction for acetylene and the rate of the reaction of hydroquinone, because both of them equal each other. So the rate of reaction of acetylene is -1/2, the change of acetylene over time. The rate of reaction of hydroquinone, there's 1 here, so it's 1/1, the change in hydroquinone over time. So right now, how you get the acetylene alone over time? You get rid of the 1/2. How you get rid of 1/2? Multiply the whole equation times 2. And that will give you your reaction disappearance of acetylene versus hydroquinone. So this is the first idea, is how to relate the different reactant to different product. And as I said, you can relate them to each other using, again, this model here. So this model here is very important because this model shows how they're related to each other, how the reactant is related to the product. And you can relate them to each other, as I showed you here. If you're looking for NO2, then you need to get rid of the 1/4, which means multiply the whole equation times 4. If you want to relate the N2O5, then you want to get rid of the 1/2, which multiply the whole equation times 2. Oxygen, you don't have to multiply by anything because oxygen already has 1. It's just already 1 mole, as you can see from the chemical reaction. So, all right. So this is the first part, which is how you write the reaction rate. Now, the second part, which is how can you define any chemical reaction through chemical kinetics? And that can be obtained by defining the rate law. So the rate law is how the reaction is related to the reactant concentration. And it is the fundamental of chemical kinetics. The rate is direct proportional to concentration. You increase the concentration, you increase the rate of the reaction. However, that direct relationship is complex in nature. What I mean complex in nature? I mean it's not just a straightforward raised to power 1. A and B is not raised to power 1. A and B are raised to power M and N, which is order of A and order of B. So there is an actual number that A is going to affect the rate with. There is an actual number or actual power B is going to affect the rate with. So it's not just a direct relationship. It's a more complex than that. And that will lead us to the general rate law. So this general rate law, rate equal K. If you remove this proportionality and you put a constant, this is how you write this law. So rate will equal K, which is a constant. And that constant is known as the rate constant. A to the power M, B to the power N. A and B is the reactant concentration. M and N is the order of A and B respectively. So this is again the order of the reactant A and order of reactant B. What is the overall order? M plus N. So the overall order will be M plus N. So this is the general rate law. And K is the rate constant. Reaction is mth order in A, nth order in B, overall order M plus N. So again, so this is how we define any given chemical reaction, is through the reaction rate. And by writing that reaction rate, we are basically looking into that reaction, chemical reaction through the kinetic of that chemical reaction.